Welcome to my video lecture. This is Amarnath, Assistant Professor in Mathematics, Department of Humanities and Sciences. Today's topic, inverse of a matrix, Gauss-Jordan method, under the course Matrices and Calculus. So in the previous lecture, we have studied about a normal form, then how to find the rank of a matrix using normal form. In the present lecture, we are going to introduce the inverse of a matrix, inverse by Gauss-Jordan method, and some problems on the matrix how to find inverse using Gauss-Jordan method. Intermediate level, we used to find inverse of a matrix using the determinant method, that is A inverse is equal to, so I think students can remember this one, A inverse is equal to, that is adjoint of A by det A. So this method you have done in the previous classes, finding 2 by 2 matrix, 3 by 3, max you can use 4 by 4 matrices. But here coming to the higher order matrices, using this determinant concept is little bit typical, because finding a determinant and finding adjoint of A, it becomes laborious. So that's why here we are introducing a new method called Gauss-Jordan method, where we don't use the determinant, just we use elementary row operations, that is called Gauss-Jordan method. So today's topic, inverse of a matrix using Gauss-Jordan method. Before that one, let us discuss some key points on the inverse of a matrix. Generally, inverse of a matrix we used to find for square matrices. Square matrices means n cross n. 4 by 4 matrix, 3 by 3 matrix, or 2 by 2 matrix. So where number of rows and columns are equal. For such type of matrices we are going to find. And one more thing, inverse does not exist for singular matrices. What do you mean by singular matrices? Singular matrix means singular. Det of the matrix is 0. So for these matrices, we cannot find the inverse. Just we can find inverse for only for non-singular matrices. What do you mean by non-singular matrices? Means det A, where determinant is not equal to 0. Why? Because just now we discussed the formula. A inverse is equal to adjoint of A by det A. So here, suppose denominator is 0, the inverse does not exist. That's why singular matrices we cannot find the inverse. Only for non-singular matrices and square matrices we find the inverse. And the second point, so inverse of a matrix is unique. One and only one inverse will exist, not more than one. However you find, what method you find, whoever they find. So inverse will be unique, not more than one for any non-singular matrix. And this one, the definition, A into A inverse, any matrix, if you multiply with its inverse of the matrix, you will get a identity matrix of the same order. Okay, this is and some more properties we used to discuss. A inverse, whole inverse is equal to, again, A. AB whole inverse is equal to, so B inverse into A inverse. So this type of properties also we know very well about the inverse of the matrix. This is a recap. Now let us go for the inverse of a matrix, Gauss-Jordan method, or sometimes we may call it as elementary row operations. Inverse of a matrix by elementary row operations or Gauss-Jordan method. Both are same. And sometimes in the examination mention Gauss-Jordan method, sometimes we say elementary row operations. What are the elementary row operations? Here you can't apply the column operations, only row operations. Only row operations you can apply. Interchange of 2 rows, and 1 row can be added to another row, or 1 row can be multiplied by any non-zero constant number and added to the some other row. This type of 3 operations we have discussed in the previous classes. That 3 defined operations only we can apply. Now, what is the working rule? How to find inverse of a matrix? For the given n cross n matrix, suppose A is a matrix, he has given n cross n. We will write A is equal to I into A same order identity matrix. The 2 by 2 I2, 3 by 3 given matrix, then I3 we will take. 4 by 4 is given, we take I4 into A, because we know very well I into A is equal to A. Means A is equal to A only, LHS is equal to RHS. So LHS A is there, RHS I into A, again A only. Here we apply the only row operations on the LHS at this matrix and we reduce to I. I means principal diagonal elements are 1 and remaining elements are 0. And what to apply? Only row operations. Simultaneously, same identical operation or row operation apply on the prefactor of this IN. Here also we have to apply. Suppose here 2 rows interchanged. Here also 2 rows should be interchanged. Here R2 plus R1. Here also R2 plus R1. Same identical operation. On post factor, no changes. So whatever the operations we apply in the LHS, in RHS pre-factor also we have to apply. Finally, here we get in the form I is equal to A into some other matrix. This will be definitely will be getting changed. Automatically here it is I means definitely this could be A inverse. So which is our required. A into A inverse is equal to I. After the row transformation, the obtained matrix is called here A inverse. That is a required inverse of the given matrix. So key point to be remembered, only row operations can be applied to find the inverse using Gauss-Jordan method. So nowhere you should not apply the column operations. So this is a new matrix I is equal to BA we are calling, or this B will be the inverse of the matrix. So here it is clearly mentioned this B is the required inverse of the matrix. So for verification, obtained matrix and given A inverse and A multiply, you will get I. Let us go for the one problem and we discuss this Gauss-Jordan method. Now here I have given a 3 by 3 matrix is given, right? So it is given as a matrix. So let us write here A matrix is A is equal to solution as per the Gauss-Jordan method. In find the inverse by Gauss-Jordan method. By Gauss-Jordan method. Or elementary row operations or only row operation. However you call, that is same. Okay, solution. So what is the procedure? As per the procedure, write at a given matrix IA. So A is given 3 by 3 matrix. So here also we write I3 and A. Right? A is equal to I3A. So here A means the given matrix. What is the given matrix? Minus 2, 1, 3, 0, minus 1, 1, 1, 2, 0. LHS given matrix. RHS I3. Identity matrix of order 3. 1, 0, 0, 0, 1, 0, 0, 0, 1. We know very well about identity matrix. A, you are not doing any changes, just write A itself. The coefficient matrix you write, there will be no change. Now, using only row operations, applying only row operations, applying only row operations, only, say remember this point, only row operations. That is a key point here. Now using the, what is the procedurality we have to do while doing the, reducing the two identity matrix. Here I will give you a small hint for you. What is that one means? Look at this in the one more slide I am giving here. Look at this one. Here I am giving the matrix using the first diagonal element, make the below two elements 0. Next, second principal diagonal, make above element 0, below element 0. And using principal diagonal, third principal diagonal element, make above two elements 0. Only which operations? Row operation. Suppose the pivoting element, if the diagonal element is 0, interchange and get the non-zero element. So this is a procedure. Once again I am explaining. First diagonal element, make below two elements, applying 2 or 3. How many are there? 3 by 3, 2, 4 by 4, 3. Second diagonal element, above element 0, below element 0. And using principal third diagonal element, it should be non-zero. Above two elements 0. And below element 0. Fourth diagonal element, make above 3 elements 0. So automatically the diagonals you will get some numbers. If you are getting 1, well and good. If not, divide with the same number at the last step. Suppose 3, 2, 4, 1. Divide by 3, divide by 2, divide by 4, divide by 1. So that principal diagonal elements will be 1, 1, 1. Automatically it becomes diagonal elements. Right side, you will be getting the required inverse matrix by applying the same row operations. Right? So here I am doing the same thing. Using the first element, make the below two elements 0. So what are the operations then? R2 implies R2. So R2 is already 0. Then let us make R3. R3 implies R3 plus. So R3 is 1 multiplied by 2. 2 into R3, 2. Our element is minus 2. 2 R3 plus R1. 2 into 1, 2. 2 minus 2, 0. So first row, no change. Minus 2, 1, 3. Second row, already 0 is there. That's why we are not doing any change. 0, minus 1, 1. Third row. So 2 into R3. 2 into 1, 2 minus 2, 0. 2 into 2, 4. 4 plus 1, 5. 2 R3. 2 into 0 plus 3, 3. So same operation we have to apply here also. Whatever the row operation, in the here also, right? 2R3 plus R1. So first row no change, second row no change, keep it as it is. First two rows as it is I am writing. Next, 2R3, 2 into 0 plus R1, 1, 0 plus 1, 1. 2R3, 0, this element, 0 plus 0, 0. 2R3, 2 into 1, 2, 2 plus 0, 2. Right? Now, the first task completed. At a first diagonal element, make below two elements, we have done 0. Next, second diagonal element. Coming to second row now. Using R2 element, we have to make R1 element 0 at here, this one. So, using R2 element, we have to make R1 0, 0, R3 0. Now, so R1 implies R1 is 1. So, multiplied by 5 to get 5. 5, sorry. So, these are using R2 now. So, R1 is 1, R2 is minus 1. That is R1 plus, pivoting element is minus 1. So, minus 1 plus 1, R1 plus R2. Minus 1 plus 1, 0. Now, R3. R3 element is 5. Pivot element is minus 1, second row element. So, R3 is 5. So, opposite signs plus 5 R. So, R3 is 5 and 5 into R2. R3 at a 5, 5 minus 5, 0. So, first check the operations and apply. First row we are changing R1 plus R2, minus 2 plus 0, minus 2. So, 1 minus 1, R1 plus R2, 1 minus 1, 0, R1 plus R2, 3 plus 1, 4. Next, R3 plus 5 R2. So, 0 plus 0, 0. So, second row we are not doing any change as it is. R3 we are changing, R3 plus 5 R2. So, 0 plus 0, 0. 5 plus 5 into minus 1, minus 5, 5 minus 5, 0. R3, 3, 3 plus 5 into 1, 3 plus 5, 8. Now, same operation here, prefactor of RHS. First row, R1 plus R2, 1 plus 0, 1, 0 plus 1, 1, 0 plus 0, 0. Next, second row we are using, which row we are using that should not be changed. Second row we are using, no change, 0, 1, 0. Third row, R3 plus 5 R2, 1 plus 0, 1, 0 plus 5 into 1, 5, 2 plus 0, 2. Right? So, here we can do half, second half I am doing. So, here 1, 1, 0, 0, 1, 0, 1, 5, 2. Right. Now, first task completed, second task using second diagonal element, above element 0, below element 0. See, using, so first task completed, second task completed. Now, using the third diagonal element, at using 8, we have to make R1 0, R2 0. Okay, na? So, this one we have to make, these two elements we have to make 0. At using R3, make R1 0, R2 elements 0. Now, look at the operations. So, this is 4. 4 means R1 implies 2R1. 2 into 4, 8. 8 minus 8, 0. So, 2R1 minus R3. Next, R2 element. What is R2 element? 1. So, make it 8 times. 8 R2 minus R3. 8 into 1, 8. 8 minus 8, 0. So, applying on the matrices. First row. 2R1, 2 into minus 2, minus 4, minus 0, minus 4. 2R1, 2 into 0, 0. 2R1, 2 into 4, 8, 8 minus 8, 0. Second row, 8R2, 0 into 0, 0. 8 into minus 1, minus 8, minus 0, minus 8. So, operation, look at the operation, 8R2, 8 into 1, 8 minus R3, 8, 8 minus 8, 0. Next, third row we are using. So, no change in the third row elements. So, third row should be copied 0, 0, 8. Right? Next, which is equal to. So, same operations, the same identical operation, same operations should be applied on RHS prefactor also. Now, first row, same operation, R1 plus R2, 1 plus 0, 1. 2R1 minus R3, sorry, 2R1 minus R3. So, that is here 2 into R1, 2 into 1, 2 minus 1, 2 minus 1, 1. 2R1, 2 into 1, 2 minus 5, 2 minus 5, minus 3. Next, 2R1, 2 into 0, 0 minus 2, minus 2. Right? Next, 8R2, 8 into 0 minus 1 minus 1. 8 or 2, 8 into 1, 8. 8 minus 5, 3. 8 or 2, 8 into 0, 0 minus 2, minus 2. Right? Next, coming to the third row. We are using the third row, that's why there should be no changes in the third row. That is what is the third row elements 1, 5, 2 into A. So 1 minus 3 minus 2 minus 1, 3 minus 2, 1, 5, 2. Now here see it is a diagonal matrix. But identity matrix means the diagonal elements must be 1. So divide with the same number all the elements. For minus 4 divided by minus 4, minus 8 divided by minus 8, 8 divided by 8. So automatically you will be getting the identity matrix. So R1 implies R1 by minus 4. R2 implies R2 by minus 8 on both sides. Right? So first one minus 4 divided by minus 4. Minus 4 by minus 4, 1, 0, 0. Second row divided with minus 8, 0. Minus 8 by minus 8, 1, 0. Third row R3 divided by 8. Because we have thought we have 8, 0, 8 by 8, 1. So same operation to be applied in the left side. And right side, here this matrix we are applying. First row divided by minus 4, 1 divided by minus 4, minus 1 by 4. Minus 3 by minus 4, 3 by 4. Minus 2 by minus 4 at a 1 by 2. Second row divided by minus 8, minus 1 by minus 8, 1 by 8. Minus 3 by 8 divided by minus 8. Minus 2 by minus 8 at a 1 by 4. Next, third row divided by 8, 1 by 8, 5 by 8. Next, 2 by 8 at a 1 by 4. Right? Into A. Now look at this one. It is a clearly I is equal to A inverse into A form. Because I, when it is possible, where definitely it will become A inverse. So what could be the A inverse means? This matrix what we have written. So this matrix is a required A inverse. So minus 1 by 4, 3 by 4, 1 by 2, 1 by 8, minus 3 by 8, 1 by 4, 1 by 8, 5 by 8, 1 by 4. The required A inverse of the given 3 by 3 matrix. Here we did not use the adjoint matrix, we did not use the determinants, only elementary row operation. Left side matrix we reduce it to identity matrix. Right side prefactor will become as our RHS by applying the same row operation. It is a 3 by 3. Let us go for the one more matrix 4 by 4. And now look at this inverse by 4 by 4 matrix. It is a little bit lengthy one compared to 3 by 3, 4 by 4, a little bit typical. With a good concentration, we need to answer the question. The procedure is same by elementary row operations or Gauss-Jordan method. By elementary row operations, he may call, or sometimes he may call Gauss-Jordan method. Gauss-Jordan method. Whatever he call, we need to apply only a row operation. Gauss-Jordan method or this one. Right now. So what is the procedure? As per the procedure, write A is equal to IA. Okay. But which order matrix? It is a 4 by 4 matrix. This should be 4. The given matrix is 4 by 4. So that's why what should be taken identity matrix at the right side 4 by 4. So left side we will write the given matrix minus 1, minus 3, 3, minus 3, 3, minus 1, 1, 1, minus 1, 0, 2, minus 5, 2, minus 3. Next, minus 1, 1, 0, 1. The 4 by 4 matrix. Into identity right side IA at a 4 by 4 identity matrix 1 0 0 0 1 0 0 0 0 1 0. Everybody knows what is the 4 by 4 identity matrix. Into A. Now apply which operations to applied? Only row operations. Here I am not writing. So you know only we have to apply the only row operations on the left hand side and reduce to identity matrix. At a principal diagonal elements are 1, remaining elements are 0. So here I said already how to do that one, using the first diagonal element, using first element. If it is 0, we will interchange. Non-zero with that element we can do. Here it is a -1. Using -1, using the R1, we make below 3 elements 0. Then second principal diagonal, make above and below element 0. Third principal diagonal element, above 2 elements 0, below element 0. And fourth element, make above 3 elements 0. Every time we take principal diagonal elements to make the above and below elements 0. That is Gauss-Jordan method. Now you see, look at the operations using R1 -1. We have to make other elements as 0, right? R2 implies R2 and R1 is -1 plus 1 at R2 plus R1. -1 plus 1 0. R3 is 2 at a 2 R3. 2 into, so R3 is 2, so R3 is enough. So R3 is 2. R3 plus 2 R1. Because this is 2, 2 minus 2 0. R4 is -1 and R1 also -1. Just subtract, it will become 0. R4 implies R4 minus R4 plus, because so same element means minus R4 minus R1, right? Okay, so first element R2 plus R1, R2 plus R1, R3 plus 2 R1, R4 minus R1, R4 minus R1, right? Now applying first row, we are using no change, -1, -3, 3, minus. Which row we are using, that should not be changed. Most of the students, they will do different rows, not possible. First row you are using, only with the first row only we have to make other elements, other rows are 0, because other elements are getting changed. You can't use that row. Any one constant row should be used to apply the row operations. Now second row, R2 plus R1, R2 plus R1, 1 minus 1 0, 1 minus 3 minus 2, -1 plus 3 2, 0 minus 1 -1. Next R3 plus 0, R3 plus 2 R1, R3 plus 2 R1 0, -11, 8, -5. Next R4 minus R1, -1 plus 1 0, 1 plus 3 4, 0 minus 3 -3, 1 plus 1 2. Okay, so 0 4 minus 1 -1 -3 3 -1 0 -2 2 -1 0 -11 8 -5 0 4 -3 2. Now same operation to be applied in the prefactor of RHS. Same operation, R2 plus R1, 1 plus 0. So first row we are using no change. Second row, R2 plus R1, 0 plus 1, 1, 1 plus 0, 1, 0 plus 0, 0, 0 plus 0. Next, R3 plus 2 R1, R3 plus 2 R, 0 plus 2, 2, 0 plus 0, 0, 1 plus 0, 1, 0 plus 0. So R4 minus R1, 0 minus 1, -1, 0, 0, 1 minus 0, 1. Okay, 1 0 0 2 1 0 0 2 0 1 0 -1 0 0 1. Right? Next. So first task completed. Using first diagonal, these tasks completed. Second. So how to do the second one? Using second principal diagonal, make above element below 2 elements 0, using only row operations, right? So first row, R1 interchange 2R1, 2R1 minus 3R2. Why? Because 2 into -3 6, 3 into 2 minus 6, minus of minus plus 6, -6 plus 6 0. Next, R2 we should not change because we are using R3 is 2R3, 2 into -11, reverse multiplication, 2 11 no common factor, 2 into 11 12, 11 into 2 12. So 2R3 minus 11R2 plus 22 minus 22 will become 0. R4, R4 is 4, so we have to make it double, R4 plus 2R2, R4 plus 2R2. So first row, 2R1 minus 3R2, 2 into -1, -2 minus 0, right? 2R1 minus 6 plus 3R2, 6 minus 6 plus 6, 0, right? Next, 2 into 3, 6, 6 minus, so here 2 into R1, 2 3 ja 6, minus 3 to just 6. 6 minus 6, 0. 2R1. 2 into minus 1. Minus 2 plus 3. Minus 2 plus 3. 1. So carefully we need to answer. Second row we are using no change. 0, minus 2, 2, minus 1. Third row 2R3 minus 11R1. 0 minus 0, 0. 2R3. 2 into minus 22. Minus 22 plus 22. 0. 2R2. 2 is 16. 16 minus 22. 16 minus 22 minus 6. 2R3. 2 into minus 5. Minus 10 plus 11. Minus 10 plus 11. 1. Next. R4 plus 2R2. 0 plus 0. 0. 4 minus 4. 0. Minus 3 plus 4. 1. And R4 2. 2R2 minus 2. 2 minus 2. 0. Right. Now applying the same operation on the right hand side. So here I am writing directly what we are getting. Applying same operations here. Minus 1, minus 3, 0, 0, 1, 1, 0, 0, minus 7, minus 11, 2, 0, 1, 2, 0, 1. So here I am writing directly. So what are the elements we are going to get by applying the same operations, right? Next. So first task completed, second task completed. See, above element 0, below element 0. Now using R3, using minus 6. So already R1 is 0. This R2 element we have to 0 make, and R3, R4 element also we have to make 0. So R2 implies R2 is 2 multiplied by 3, 3R2. 3R2 plus R3. Next, R4 implies 6R4. 6 into 1, 6, 6R4 plus R3. We are using R3 this time. Okay, now. So using R3 we have making above element 0, below element 0. Already R1 element is 0. So first row no change. Minus 2, 0, 0, 1. And second row we are changing, that is 3R2, 0 plus R3, 0. 3R2, 3 into minus 2, minus 6 plus 0. 3 into 2, 6, minus 6, 0. 3R2, 3 into minus 1, minus 3 plus 1, minus 2. See the operation, 3R2 plus R3. Next, R3 we are using. So R3 no changes. So previous row here, 0, 0, minus 6, 1. 0, 0, minus 6, 1. We are writing. Next, 6R4 plus R3. 0 plus 0, 0. 6R4, 0 plus 0, 0. 6R4, 6 into 1, 6 minus 6, 0. 6 into 0, 0 plus R3, 1. So 000, 1. So this element. Now same operation. Our first row no change. We should apply on the prefactor. That is minus 1, minus 3, 0, 0. Second row, 3R2 plus R3. So by applying this one, we get minus 4, minus 8, 2, 0. Next, third row we are using. Third row we are using means no change. Minus 7. And here whatever we have, minus 7, 11, minus 11, 2, 0. No change. Next, 6R4 plus R3. 6R4 plus R3 means minus 1, 1, 2, 6. Right? Into A. Next, see, first 3 tasks completed. See, these elements also done 0. This first task completed, second task completed, third task completed. Now using R4, D4, we have to make this element 0, this element 0, above 3 elements we have to make 0. So what are the operations? Simply subtracting R1 minus R4. R2 implies R2 plus 2R4. Next, R3 implies R3 minus R4. R4 we are using. So in the next slide we will write this one. These operations we will write in the next slide. Now look at this one. What we are getting, applying that same operations I am writing here directly. Right? Minus 2, 0, 0, 0, 0, minus 6, 0, 0, 0, 0, minus 6, 0, and 0, 0, 0, 1. So applying the same operation on the prefactor. The getting elements 0, minus 4, minus 2, minus 6, and minus 6, minus 6, 6, 12, and minus 6, minus 12, 0, minus 6, and minus 1, 1, 2, 6. See, but see, look at this one. Here diagonal elements are not 1. So we want to make this matrix as identity matrix. So divide with the first row, divide with minus 2, second row divided with minus 6, third row divided with minus 6, fourth row already 1. So you need to make change. Automatically divide by minus 2 means here that is a 1, 0, 0, 0, 0, 1, 0, 0. Second row we are dividing with minus 6 at a 1. So 0, 0, 1, 0, 0, 0, 0, 1. So same operation at the right side. So first row divide with minus 2, 0, 2, 1, 3. Second row divide with minus 6, right? 1, 1, minus 1, minus 2. Second row divide with minus 6, third row divide with minus 6. Minus 6 means 1, 2, 0, 1. Fourth row already is 1, we are not doing anything. Same element, minus 1, 1, 2, 6, right? Into A. Now clearly it is in the form of I is equal to something into A. Definitely it could be A inverse. So what could be this could be our required A inverse, right? So required A inverse for the given matrix, right? 0, 2, 1, 3, 1, 1, minus 1, minus 2, 1, 2, 0, 1, minus 1, 1, 2, 6. Okay, this is the A inverse of the matrix, right? So only raw operations carefully we need to answer. So here I am giving 2 problems for practice. Find the inverse. 1 3 by 3 matrix is given, 1 4 by 4 matrix is given using Gauss-Jordan method, right? So in the present lecture we have discussed about the inverse of a matrix using Gauss-Jordan method. In the next class we will start the applications of the rank finding, solution of system of linear equations that we will discuss. Thank you.